Graphing rational functions. Okay, so the approach to graphing rational functions will be first to sort of frame the picture with any asymptotes and any holes that the graph might have. So the first thing that we want to do is we want to make sure that our original function is factored completely, and this one isn't. So let's factor x minus 1 over x plus 2, x minus 2. It's just a difference of squares here. So we want to be looking for any vertical asymptotes, any holes, any horizontal asymptotes, and if there isn't any horizontal, whether there's a slant asymptote. So the first thing I'm looking for are common factors that show up in both the numerator and denominator, because that would indicate a possible hole. So there isn't. X plus 2 doesn't show up there, and x minus 2 doesn't show up there. So that means that both of these are vertical asymptotes and that there's no holes. So x equals negative 2 and x equals positive 2 are both vertical asymptotes. Now for the horizontal or possibly the slant asymptote, I need to look at the degrees. The degree in the denominator is larger, so that means that the horizontal asymptote is y equals 0 and there will not be a slant asymptote. So going forward, what we're going to want to do is graph any asymptotes and any holes that we might have on our graph. So the vertical asymptotes, I'm going to have x equals negative 2. So do that. X equals positive 2. And y equals 0, which is going to be the x-axis here. Okay, so it's now framed up for us pretty nicely here. So the next thing that you want to do is you want to solve for any x-intercepts and any y-intercepts that there might be. Now the general rules to setting the x-intercepts or finding the x-intercepts and y-intercepts are as follows. For the x-intercept, what you want to do is set the numerator equal to 0 and solve for x. So for this problem over here, I'm going to set the numerator up equal to 0 and solve. So I get x equals 1. That's my x-intercept. So that means when x is 1, it intercepts the graph. Now let's look at the rule for the y-intercept. For the y-intercept, you set all x's equal to 0 and solve for y. So for this one, it's going to, let me just put this down a little bit here. So I would have y equals, I'm going to set the x is equal to 0. And you can use the original here or this one, it doesn't matter. So 0 plus 2, 0 minus 2. So 0 minus 1 is negative 1, 0 plus 2 is 2, 0 minus 2 is negative 2, 2 times negative 2 is negative 4, so I have 1/4. So 1/4 should be right around here, is going to be my y-intercept. So as coordinates, this x is 1, 0, and this is 0, 1/4. Now let me just explain why the x-intercept can be solved by setting the numerator equal to 0 and solving for x. You could have set y equal to 0 and solve for x. But what happens is, if I set y to 0, I'm going to have 0 equals whatever I had in the numerator divided by whatever I had in the denominator. All you're going to be doing is multiplying both sides by the denominator as a step. And if I multiply the 0 by the denominator, I'm going to have 0. And if I multiply this by the denominators cancel and I just have an n, which is the numerator. So that's the reason why the trick for the x-intercept is just skipping all of that and going straight for the numerator and setting that equal to 0 and solving. Okay, so the next step for this problem is going to be looking at where there's critical events that occur to the x-axis. So if I'm looking at any vertical or slant asymptotes that cross through it, or any x-intercepts, something happens here at -2. It's a vertical asymptote. Something happens here at 1. There's an x-intercept. And something happens here at 2. I have a vertical asymptote. So what you're going to do is you're going to just draw a line here. It was -2. Let me just grab back up here. -2, 1, and 2. 1 and 2. The 1 had an x-intercept. The other 2 had vertical asymptotes. What you essentially have here is intervals. You have this interval here, which extends from you could say -infinity all the way to -2. That would be interval 1. And then from -2 to 1 is another interval. 1 to 2 is another interval. And then 2 to positive infinity would be another interval. What you need to do is you need to pick a point, an x coordinate, or an x value, in each of these intervals. You need to find out what's happening to the graph within each sort of critical area and beyond it. So what I'm going to do is I'm going to choose like -3. I'll choose that. I'll choose let's do -1. Let's choose 1.5, so 3 halves. And let's choose 3. So what I'm going to have to do now is essentially find out where the coordinates are when x is -3, -1, 3 halves, and 3. So let's do that. So our function was x minus 1 over x squared minus 4. We can use that, or we can use the factored version. It doesn't really matter. So let's find out. So -3, we want to find out when x is -3. We want to find out when x is -1. We want to find out what happens when x is 3 halves and when x is 3. So we're going to have 4 coordinates here. So when x is -3, we're going to have -3 minus 1 over -3 squared minus 4. So this is going to be -3 minus 1 is -4. -3 squared is 9. 9 minus 4 is 5. So we're going to have -4/5 here. Alright, for -1, I plug -1 wherever I see an x. So I'm going to have -1 minus 1 over -1 squared minus 4. So -1 minus 1 is -2. Negative 1 squared is 1. 1 minus 4 is negative 3. So negative 2 over negative 3 is 2/3. Let's do 3/2 now. So we have 3/2 minus 1 over 3/2 squared minus 4. 3/2 minus 1 is 3/2 minus 2/2, which is 1/2, over 3/2 squared is 9/4. So this is 9/4 here. Minus 4. If I convert that to fourths, I'm going to have 16/4. 9/4 minus 16/4 is negative 7/4. So if I have a division of fractions here, I have 1/2. Because I'm dividing, I'm going to invert and multiply. So times negative 4/7. So I'm going to have negative 4 over 14. And let me just fix that. It's going to be I can cancel the 2 and the 4 here, so I have negative 2/7. Just want to write it as reduced as you can. And then lastly, find out what happens when x is 3. So 3 minus 1 over 3 squared minus 4. 3 minus 1 is 2. 3 squared is 9. 9 minus 4 is 5. So we have 2/5 here. So we're going to take these 4 points and we're going to plot them on our graph. So negative 3, comma, negative 4/5. So negative 3, negative 4/5 is almost at negative 1. Negative 4 over 5 is negative 0.8. So I'm going to have it right around here. The next one we had is negative 1, comma, 2/3. So negative 1, comma, 2/3. So 2/3 of the way up, right over here. The next point we had was 3/2, which is 1.5, comma, negative 2/7. So 1.5, comma, I forgot, it was negative 2/7. Okay. So negative 2/7 is not quite negative 1/2, so right around here. And lastly, 3, comma, 2/5. So 3, comma, 2/5 is right around here. Alright, so there's a lot of points here. Now, in order to actually get this full graph, you have to sort of understand what the asymptotes do to the graph. So the areas that you really want to focus on for asymptotic lines are the extremes of the asymptotes. So way to the left and way to the right, all the way up and all the way down. Those areas are really important because it's at the extremes or the furthest location of the asymptotes, and they all go to positive and negative infinity, but it's going to pull the graphs toward it. So for example, this graph over here, not this graph, but this part of the asymptote is going to pull this toward it. So I know for a fact it's going to pull the graph ever so close to it. And this comes down and it hits that point, and then what this part is going to do, it's going to pull the graph toward it down here. So you have this sort of bend in the graph. It almost looks like you're sort of merging on the highway coming off of an exit. You're merging onto traffic. Now over here, we have the extremes up here are going to pull the graph. And we see here that we've got this sort of thing going on. Now this down here is going to pull it down, and it's going to get infinitely close to it, but it will never hit it. And this part over here is going to pull it toward it, and it's going to look like that, sort of a swoop in here, and it comes all the way down. And lastly, this part, it's going to pull this toward it, and this is going to pull it up here. So this is what the graph of this function looks like. So just a really quick review. When you're graphing rational functions, the first thing you want to do is you want to make sure that you factor the function as much as you can. Then you want to break it down and find all the asymptotes and holes, and you want to put that on your graph. That's sort of the framework for it. Then, using the simplified version of the graph, in other words, if you did have an x minus 2 in the numerator and denominator, you would just cancel them and use the simplified version of the graph to find the x and y intercepts, if there are any. After you find the x and y intercepts, you plot those on the graph. After that, you want to break up the x-axis into intervals. And the things that you want to focus on in terms of the intervals, or I should say the things that break up the x-axis into intervals, are vertical asymptotes and slant asymptotes, because they cross the x-axis, in addition to any x-intercepts. Those are the things that break up the interval, or break up the x-axis into intervals, I should say. Then once it's broken up into intervals, you choose a point or an x value within each of those intervals, and you find out the points for those. Those points then go onto the graph, and then you want to use the extremes of the asymptotic lines to pull and form your function.